Good afternoon, everyone. My name is Runhai Ouyang from Fraser Harbor Institute. I will be introducing a newly developed method, SISSO, for searching for material descriptors. So I start with some words by some physicists. So scientific discovery often proceeds from the accumulation of consistent data to the identification of functional dependence among the data. For example, a model that is able to predict yet unseen phenomena, and ultimately a theory may be constructed to explain the model with few simple principles. And it's set by Matthias Scheffler. So here is an example, the discovery of the law of planetary motion. So we know that Tycho Brahe spent his lifetime on the astronomical observation and passed his data into Kepler's hand on his death. Then Kepler did the data analytics, and he spent 4 years tested tens of orbits and finally discovered the elliptical orbit. And we note that at that time the least square was not yet invented. Another example is the periodic table of elements. And for the data accumulation, new elements were discovered at the rate of 1 per year, and up to 56 were known by 1863. Then Mendeleev did the data analytics, and he envisioned his periodic table in a dream in 1869. So we see data analytics is important for scientific discovery, but if we can't get a result from dreams, then we need to develop a method to speed up the discovery. Okay, so nowadays in material science, we don't need to spend the whole lifetime to collect data, and we already have big data. For example, the Nomad contains 44 million of data, and the flow 1.7 million with 168 million of property calculated, and also the Springer materials with over 400,000 experimental data. So here I want to show you the state of the art of the data analytics and the machine learning. So artificial neural network, which build models in a way inspired by biological nervous system, for example, the AlphaGo. The symbolic regression, which learn a function by searching the space of mathematical expressions via genetic programming. For example, the Eureka software from this company. And also you can find many other machine learning methods from this book. Regularized regression, trees, nearest neighbor, support vector machine, and so on. But in this talk, I will focus on complex thinking. The reason is that it answers this important question, how to train a predictive model, not just a fitting. And Yang already gave a very nice talk, so I will skip this part here. Now, we applied complex thinking for material science. So for any material property, we describe by a linear model. So here the P is the material property of interest, and the C are the coefficients, the F are the features, which are nonlinear functions of basic input variables. Then we define the vector to be the set of features with the coefficient not 0. Here is the workflow. So first, we perform uniform sampling of the signal or the material property P in the whole material space. Then we construct a feature space for the description of the property P, and then we do the specification of the linear model, or the descriptor identification. Here I show you how we construct a feature space. So first, we need input of an initial feature space which contain the input variables, or we call it primary features. Also, we need an operator set so that we can transform the basic variable to expand the feature space. And here, the output, so phi n, the feature space of rank n. So the idea here is that we apply the operator set to phi 0, we get phi 1. We apply to phi 1, then we get phi 2. And so for any phi n, we take the union of feature space from phi 0 to phi n minus 1. And we note here the script here, m, indicate meaningful combination. For example, we don't do the size plus energy with the plus operator. And for unary operator, for example, the log, the exponential, it only applies to the phi 1. And here, we can know the size of any feature space phi n. For example, if the phi 0, the size of phi 0 is 10, and the number for binary operator is 5, then we will have the phi 3 with the size of 10 to the 12. So it's a huge feature space. That means we need a good method to manage huge feature space for the sparse solution. And here are the popular specifying operators. So formally, the L0 should be used because it can give the global optimal solutions. However, it only limited to small feature space because it is NP hard, as Jiang has introduced it. The last law can apply to large feature space, but they usually give poor solution when features are correlated. And also greedy algorithms such as the orthogonal matching pursuit, OMP, they are applicable to huge feature space, but usually end up with local optimum. So we need a better method for finding sparse solution.
Sorry, just a question to connect
Yes.
to the previous talk. So your second point for solution when features are correlated, was that what the previous speaker said when there was this over determination with the x1, x2, so that you had different.
Yes, so here the correlated means coherent feature space. So when features are highly correlated, I mean,
Distinguish which one.
yes, they are non-orthogonal, then they will have a problem to identify the best solution. Then we propose the SISSO, a new method, which combines sure independent screening and specifying operators. So here the SIS is a dimension reduction method, which select a feature with the metric to be the inner product between the target property and any features. So for example here, the property P, we calculated the correlation of all the features with the P and selected the highly correlated features with the P. So suppose we have a huge feature space, then we start by Cs to select a subspace which has a modest size, so that the lower dimensional model selection method can be applied. For example, the L0 or last or L2. Then from the subspace, we apply the SO to find the best 1D descriptor. Here 1D means only one non-zero coefficient in the comprehensive model. And then we check the leftover, the residue. If the residue is still large, then we will go back to the huge space and do the Cs again. But now we replace the target property by the residue and select the second subspace. For example, here, so with the 1D descriptor, we calculate the residue and then Cs selected the second subspace, which has a good correlation with the residues. And then from the union of all the selected subspace, we apply SO again to find the best 2D descriptor. And we do this until step N, which can get a descriptor that hit the quality requirement. Now let's see a benchmark descriptor identification for structural stability. So here the property is the energy difference between the two structures. And for the training data, we take 82 energy difference between energy difference of binary materials from DFT calculation. And for the primary feature, the input variables, they are atomic parameters, for example, the ionization potential, electron affinity, and so on. And all the data are obtained from the nomad repository or this paper. Now let's see the performance of SISSO. So here I show you the training error against the descriptor dimension by different SO method. So here the orange down triangle is the lasso, and the up triangle lasso L0, and the green OMP, blue is the L0, all with the same feature space. So we see lasso indeed give very poor result because the correlation between features. And the lasso plus L0 and OMP have a better solution, but the L0 of course give the best. However, even if for the best solution by L0 we see there is still a large training error higher than 40, then we would like to try larger feature space to reduce the training error. So we compare the SISSO with the OMP. So here is the training error against the subspace size by SIS. So we see the SISSO with the SO to be L0 give much better result than the MP with the subspace size. But this is not the case for SISSO with SO to be the lasso plus L0 because of the failure of lasso. Here we use the same phi tool which contains 10 to the 5 features. We further apply the SISSO, well SISSO means L0 to phi 2 and phi 3, where the phi 3 contains 10 to the 11 features. So we see the descriptor has a systematically lower training error than from the phi 2. And also we compare our result to previous work. So we see our result systematically improved over this work. We also compare our result to that obtained from the commercial software Eureka, which evaluated 10 to the 12 function, has a similar size with the phi 3 here. So we compare here. So the blue circle are all well below the green line, except the first dimension here.
Could you repeat the meaning of the phi 1, phi 2, and phi 3?
Yes. So feature space construction. So here phi 0 is the input variables, right? Then we apply the operator set to phi 0, then we get a phi 1. And we apply phi 1, we get a phi 2. And finally, we find the union of all this. So we also check the maximum absolute error from the training. So we see the blue has the same trend. They are well below the orange. And moreover, for the blue circle, even for the 1D, it has a much lower maximal absolute error than the Eureka. So this result shows the SISSO has the best performance. Also, the SISSO is not only for quantitative property, but also for classification. So we define the L0 for classification of M group, where M is equal or larger than 2 in this form. So the loss function here the OIG, is the number of data in overlap region between I and G domain. For example, here we have 3 domains approximated by convex H. So here the loss function means the total data in each of the overlapped region. And the C is the sparse vector with 0 or 1 element. And the lambda here is the parameter controlling the number of non-zero elements in the C. Also, we need a metric for the C's for classification, because the C means inner product for quantitative property, but for classification, then we define the correlation to be the reciprocal of the overlap. Here we plus 1 because we want this quantity to have the range from 0 to 1. For example, here we have 2 groups, blue and red. So the number of all overlap data is 4, so 1, 2, 3, 4. Now, application of SISSO for classification, the case of metal, non-metal, we take experimental training data from Springer materials. And all the metal and the non-metal of AXBY crystal are used, which is about 300. And here, the A belongs to any element, and the B belongs to P element. And also, A has coordination polyhedron comparison of only B and vice versa. Also, we take all the stable element metal for the training. We also take experimental data for the primary feature, the ionization energy, electron affinity, atom covalent radius, electronegativity, valence, bond distance in crystal, coordination number, packing factor, atomic ratios. Now I show you how we get the best descriptor. So initially we use only materials of the same rock salt prototype, 128 materials, and here these are intuition suggested primary feature. And we can easily identify a descriptor for 100% classification. So here, the D is from the structure, and all others are the atomic parameters. Then we increase the number of prototypes up to 5, which means we include more chemical environment into the training. And the number of material 216. Then we found that this primary feature can get a descriptor for 100% classification. And until we add more primary feature, the coordination number. And this makes sense because we see different prototypes have different coordination environment. So we need this, otherwise we can't make a total classification. So with this primary feature, we again identified a descriptor for 100% classification of the data. Then we include more prototype, so up to 10, and 259 materials. We use the same primary feature as here, and also found a descriptor for total classification. This is a 2D descriptor, 2 feature, but we see this descriptor is already quite complex, and people may don't like this. Then I realized that from this descriptor and the descriptor, the pattern, the bond distance minus radius, they appear very frequently. So I realized that the packing efficiency may be, packing factor may be more efficient than this structure parameter. And indeed, when I add this primary feature into the phi 0, then I found a much simple descriptor. The same training data, same prototype, but just replace the 3 guy by the packing factor, we immediately get a very simple descriptor. Finally, we increase the number of prototypes up to 15. and also we include 64 element metal. But then again, we found this primary feature can't yet a descriptor for total classification. Then again, we realized that the atomic ratio is needed because you see here the aluminum oxide, it's A2B3 and the TH3P4, the A3B4, and here A1B3. So they have a quite different atomic ratio. So after we include the atomic ratio A and B, then again we found a descriptor that can totally classify all these training materials. So here is the best, the best descriptor for 99% to 99.2% classification of all the training data. And so you see, this domain are metal and this domain are non-metal. So we see the non-metal are defined by all the fluoride. And here the metal domain, so this is the gold and the U, AC, and the gold indium. The key parameters of the descriptor can be very well understood. For example, the packing factor, so high packing efficiency, high interstitial charge, and then high propensity of being metal. And also for this one, the ratio of the electronegativity, so high degree, the larger the value, the higher the degree of the ionic bonding, low interstitial charge, and finally high propensity of being non-metal. So by understanding this, it's no surprise to see that the lithium fluoride is at the rightmost position because this fluorine F has the largest electronegativity, and the lithium has very low electronegativity. And also for this, the gold has the indium has a larger, even has lower negativity than the gold, so it comes at the leftmost. Now we want to validate this descriptor. So normally the descriptor should be used to predict the materials under normal pressure, because in our training data there's no any high pressure data used. But we think that if the descriptor really carries some physical instead, then it can be extrapolated to high pressure. So from the database, we found 3 materials undergo the insulator metal transition. So here are the 3 materials. They are non-metal under normal pressure, and the experiment shows they are metal under high pressure. And indeed, we see that the 3 blue square are in the blue domain, and the red circle are in the metal domain. So our descriptor reproduced the experimental result. Then we make some prediction of insulator to metal transition. So here with green lines for the prediction. So each green line represents 1 gigapascal step. So for example, the silver iodide, so we count how many green bars, 1, 2, 3, 4, 5, 6, 7, 9, 10. So that means if we apply 10 gigapascal, then the silver iodide will move to here, transition from non-metal to metal. And the same for these materials. So they are very close to the boundary. So these are waiting for experiment to confirm. Finally, here is a summary of the SISSO's advantages. So first, good interpretability, because very few coefficients are involved. Biased feature construction, because we construct all the feature within certain complexity cutoff. No assumption of the descriptor functional form. We don't need an assumption before the learning, but we learn the functional form. So managing huge and coherent feature space and applicable to any material properties, including quantitative and classification problems. So I want to thank Matthias Scheffler, Luca, Stefano, Emily, and Daria. Thank you for your attention.